okay? Discrete optimization, meta-heuristics. So that's what we're going to talk about today. So we are still in local search. We have seen heuristics last time. What we're going to talk about today is meta-heuristic. I won't talk about all of them. I just want to give you a flavor of what you can do. And so I will basically talk about 3 of them, iterated local search, simulated annealing, and Tabu Search today. Okay, so the goal here, heuristic is trying to, drive you towards a local minimum. Okay, what the meta-heuristic is going to try to do is to avoid you to be stuck in a poor local minima like this one. You want to go there, right? So, but you may be stuck here. How can you escape that local minima and such a way that you can still actually go to high quality solutions? So you have this trade-off, right? So you want to be able to go up, because otherwise you're stuck into these local minima. But you also don't want to go too way far up and you never go down anymore. Okay, so you have to find this reasonable trade-off in the ability to go up outside the local minima, but at the same time you have the ability to sometimes dive in and actually get to a very high quality solution. Okay, so that's the trade-off that we need to explore. Okay, so iterated local search is a very, very simple way of trying to achieve that. Okay, so you start from a point, choom, you dive down to the to a local minimum. Okay, then you start from another place and you dive down again. Okay, so you generate another point and you start and you try to go down. And then you keep doing that, okay? So you start to have another point there and you just go down, okay? And so you do that for many, many, many different starting points. And then at the end, you essentially take the best, the best solutions that you have found, okay? So that's the key idea of iterated local search, okay? So basically, you execute multiple local search from different starting configurations, okay? It's generic in the sense that it can be combined with many other meta-heuristics that I'm going to show you later on. And it's often called, multi-start search or search with restarts and so on, okay? But the key idea is that you have a local search and you iterate it many, many times, okay? And so this is essentially the, the pseudocode for this particular iterated local search. So you generate an initial solution, okay? And then essentially, and this is the best solutions you have so far, and then you iterate a number of searches, okay? And every one of these searches is one of the local search that I've shown you in the previous lecture, right? And then at the end of the day, this will give you the best configuration that this local search has found. If it's better than the best solution so far, you keep it, okay? Otherwise, you just ignore it, okay? And then you generate a new solution and you redo another start, okay? You search again from that new starting point. Now that starting point can be completely generated, randomly, or it can use the solutions that you have found so far, okay? And there are techniques like path relinking, which are sophisticated ways to do this. But the basic idea here is that you do whatever you want, but you have to have a new starting point, which you believe, is going to be interesting, okay? It can be completely random, or it can be exploit some of the solutions that you have seen so far, or the current solutions that you have. Okay. Now, so as I said, this technique can be most of the algorithms these days in local search or in other, even when you do branch and bound or other searches, are using some form of restarts for actually improving the quality of the solutions. Okay. So what I'm going to do now is look at heuristics that are more specific, meta-heuristic that are more specific. And so I'm going to start here, I'm going to talk about simulated annealing, but I'm going to start with the Metropolis Heuristic, which is a heuristic on which you build simulated annealing, okay? And the basic idea here is the following. So you want to accept a move, obviously, if it improves the value of the objective function, but otherwise you want also to accept move that degrades the value of the objective function, but with some probability. And that probability has to be somewhat proportional to the degradation that the move is going to perform. If the move is terribly bad, you probably don't want to take it with a high probability. If it's really, really close, to improving, you want to take it with a higher probability. Okay, so the whole thing here that I'm going to talk about is inspired by results in statistical physics, and I'll come back to that later on. Okay, so this is essentially the way you're going to do. The probability is chosen using 2 things. A temperature, you can ignore it right now, so we'll talk a little bit about it afterwards. And then essentially the key aspect here is the delta, the difference between the value of the objective function of the neighbor and the current value of the objective function. Now, of course, if this difference is negative, that means that the move is improving, and therefore you take the move all the time. Okay, but if the value is positive, okay, so that means that the move is degrading, and you have to choose the probability of accepting that move, carefully. The probability is too high. You're only going to go up, and you will accept, essentially moves that are degrading all the time. So you want this balance between improving and then sometimes jumping up and moving up, okay? And that's what we are trying to do with this probability distribution. Essentially, you want to take the move with a probability which is exponential in the basically minus the delta, okay? So So remember, when the delta is positive, that means that we are degrading, okay? So this value minus the delta is going to be negative in that point, okay? So look at this formula, and then there are two things that, so this is the algorithm, and we look at the formula and actually analyze it in a moment, okay? So, but essentially what you do here, you always combine this with a random selection of the neighbor, okay? So you basically take a neighbor in the neighborhood with a, random probability, so you get this beautiful neighbor, okay? And then obviously if it improves, you take the neighbor, but otherwise if it degrades the value of the objective function, you flip a coin, with, and decide with, with this probability distribution if you accept the move or not, okay? And then if you, if you're lucky, if the coin turns well, you take the move. Otherwise, you just ignore the move, okay? And you stay where you are, okay? And so you iterate this, select another array randomly, flip a coin, decide if you take it or not, and can continue doing this, okay? Now let's look at this probability. So if we have a very large delta, okay, so look at this delta. Assume that it's very large. What's going to happen with this probability? Okay, the probability distribution that you see there. Well, this number here is going to be very negative, so the probability is going to be very small. So if you have a big difference between the current value of the objective function and the value of the neighbors where you want to move to, the probability of actually accepting is going to be tiny, okay? So you don't want to take really, really bad move, although you could, right? There is always a small probability that you're going to take it, okay? Now, let's look at this probability now, and this temperature now, okay? So if this temperature is very large, what's going to happen, okay? So if the temperature is very large, that value is going to be what? Is going to be essentially tiny, and therefore you will accept, the probability of accepting the move is going to be very, very high, okay? So essentially if you have a large temperature, you're going to accept many, 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 many moves. So which basically means that you are basically performing a random walk. So you are walking, looking around, oh, is this good or not, and then you're looking around essentially. But you accept moves that can be really bad, degrading your function tremendously. Okay, so in a sense, if you have a very large t here, okay, so what's going to happen is that you are going to have really a random walk. Okay, if you have a small t, the opposite is going to happen. If you have a tiny, tiny, tiny t, like 0.00001, okay, so that value here is going to be really negative, and therefore you only going to consider you're going to accept the move with a degrading move with very, very, very low probability, which basically means that in this particular case, you are kind of being greedy, right? So now what you have to think about is that you have this temperature, you have also the difference in the objective function, and of course that's basically specific to the particular problem that you have, and you have to kind of balance these two such that you get a compromise between accepting degrading move and then at some point being greedy enough to actually get to a local minima, okay? And so you have to balance these two things, okay? So what the simulated annealing algorithm is really trying to do is to try to achieve this balance in a dynamic fashion, okay? So it's based on material physics where you try to essentially heat and then cool, the material such that you generate beautiful crystals with almost no defects, okay? And so what you do is essentially here the key idea is that you start with a very high temperature, which means that you are essentially performing this random move, moving along, looking, is the space look here or is the space good there and so on, looking around, and then progressively you are going to cool this temperature and then becoming more and more greedy, okay? So in a sense you start with a high temperature, which is like a random walk, and then more and more you are making it more and more greedy, okay? And so when the temperature is really, really low, you are basically doing a local improvement search, okay? So essentially, the key here is that you start with a reasonable temperature, looking around, and then you decrease it such that at some point, it becomes greedy, and you focus to a local minima. So in a sense, you bounce inside the search space everywhere, and when you think that you have a very good neighborhood in that particular search, in that particular space, you dive down and try to get this good local minima, that minimum that you want. Okay, so this is the description of the search procedure in the most formal way. So what you see is that once again, it's basically a set of searches, and every one of these searches is going to use the Metropolis algorithm. It's a local search with the Metropolis algorithm. You are at a particular temperature, and then you bounce around. You look around, and you try to find, you move from state to state, configuration to configuration. Okay, so that will, at the end of this particular search, you will get a particular objective value. If it's better than the best solution you have found so far, you keep it. And then what you do is you decrease this temperature, and then you iterate the process. Okay, and the point is that at some point the temperature is going to be so low that the only thing that you will do is accepting, moves that are that are improving, and you basically converge to something which is a local improvement. Okay, so this is the basic idea with the simulated annealing. So kind of random search with a particular probability of accepting degrading move. At the beginning, the first searches that you are looking at, you essentially accept everything. You are really, looking around. And then as time goes on, you are becoming more and more and more greedy until you really converge to a local improvement search. Okay? So no, this simulated annealing, came from physicists, and it has a very interesting property actually, is that if your neighborhood is connected, okay, so you are guaranteed to converge to the global optimum. Okay, so you only need this connected neighborhood, property that I mentioned before. And if this is the case, if you have a very, very slow schedule, then you are guaranteed, in the expected sense, to actually converge to the optimal solution. Okay, the only real issue is that this is actually slower than exhaustive search. So if you actually use this really, really slow schedule, it's going to take a long time to get to this optimal value. Okay? So, but in practice, in a sense, you will never use this kind of really, really, really slow schedule where you decrease the temperature so slow that it's become boring, right? So what you are basically doing is, a temperature cooling, which is much faster. Okay? So let's say linear or geometric progressions of something like this. And once you do that, you can have really, really amazing results on some very complicated applications or benchmarks. So the traveling Tolman problem, for instance, has, the best solutions for some of the largest initial instances have been found using simulated annealing on the complex neighborhood that I've shown you before. Okay, same thing for some of the some complex problems in in scheduling where you try to minimize tardiness of various tasks. Okay, so the basic idea here is that in practice, obviously, you don't use that slow schedule, but you use a schedule which is reasonably fast. But still, the ability at the beginning to explore the search, to looking around and seeing where you should search, and then progressively narrowing down the search towards the local improvement is actually pretty effective. Okay, so that's the key idea. Now, in practice, you can add a variety of techniques, and so in some of the cases, that's what has been done on the TTP and other problems. You can always add restart. You can always start from multiple points. Okay, you can also do something which is called a reheat. If you cool too fast, you say, ooh, I'm going way too fast. Now let's step back and increase the temperature again. Look around, and then dive again. Okay, and there are also many properties of Tabu Search that I'm going to talk about in a moment that you could actually incorporate in the simulated annealing algorithm. So once again, this is an introduction. I'm giving you the basics, but there are many other techniques that you can actually use. Okay, so I talked about this already. So we can, like in a multi-start, you can always start from multiple points. It's very useful for the TTP as well, and then you can also increase the temperature if you want to at some point. Okay, now let me talk about Tabu Search now, which is the last meta-heuristic that I want to talk about today. And so I'm going to first give you the intuition, and most of the presentation in this lecture is going to be at a high level on Tabu Search, and the next lecture is going to focus on Tabu Search exclusively. But this is the idea. This is what we really want to do in practice, right? So you start with a node, and then you dive down. You get to this beautiful local minima, but it's a local minima. So what you want to do is to say, oh, can I step up now and try to find something which is better? So you decide, oh, I want to step up over there, and then you go down, again, and you say, oh, this is a better local minimum. Okay. So the problem is that this is actually difficult to do. Why? Because Tabu Search is this kind of greedy search procedure. And typically, when you are at a particular place, if you select the best neighbor, it's going to be where you are or where you have been. So you're going to stay at the same position. Okay? So what you need to do is something that essentially keep track of the nodes that you have visited. And these nodes are going to be blue. Okay? I wanted them to be yellow, but Carlton told me they have to be blue. Okay, so this is a blue neighbor. A blue neighbor is a neighbor which is essentially taboo. I have seen it already. I don't want to go back there. Okay, no, yellow was a better color, but anyway. Okay, so what we see here, we are in this particular blue state. Okay, that means I have been there. And now I can move to that particular position here. Okay, so that's fine. Now, look at this thing. Okay, see, if I had a neighborhood here, if I look at the neighborhood here, okay, and I use Tabu Search, we always want to improve in a greedy fashion, right? So I would go back here, right? So that's what I would do immediately, okay? But no, I can't do that because this guy now is taboo, okay? Taboo means I can't go back there. I have visited that node, I can't go back. So you are kind of forced to move to a node which which doesn't have as good an objective function, and therefore you move to this thing there. Okay, and once again, once you are there, Tabu Search is going to say, ooh, while local improvement is going to say, ooh, I want to go there, or I want to go there. That's better. That's where I want to go. But of course, these things are taboo, so you can't go there. So this thing is forced to go up there. Okay, and that's good because now you can go down and hopefully find the optimal solution in this particular case. Okay, so this is the abstract idea behind Tabu Search. Okay, so you maintain something which is called a tabu list. Think of it, this is all the nodes that you have visited so far, and you never want to go there again. You have been there, okay, seen that, okay? I know what these nodes are, okay? And this is a set, this tabu list is a set of tabu nodes that you have seen already, okay? So what you do is, as usual, you start from an initial state, and then we build this sequence, okay? Tau is a sequence of nodes that you have seen so far, okay? That's the tabu list, okay? That's all the states that I have seen, okay? And then you do a local search like normally, right? So if it's a number of iterations, at every iteration you take you look at the state that you are in, and if it proved the best solution so far, you take that move and it's satisfiable. That's the best solution you found. Otherwise, you generate a new neighbor, which select the legal moves, and we're going to see what these legal moves are, but they have to be moves that are not taboo, right? And then in the neighborhood, okay? And what you do then afterwards is that you increase this tau function, and the tau function has another node now that you have visited, right? So, and that's what this basically generic framework does, okay? And so when you do Tabu Search, the only thing that you do is you have to use a legal move functions that tells you the node cannot be taboo, okay? So in a sense, it's the traditional local search, but you have to say, oh, I want to select neighbors that are taboo, okay? And of course, you have this list, this tau, and you can just test if the particular states that you want to move to is, you want to test if this move is going to be legal if it's not taboo, okay? And so that's what you see here. Okay, so you basically look inside the tau. If the move is inside that tau, okay, so you know that you visited so far, you don't take it. So the legal moves are all the moves in the neighborhood that are not in tau, that haven't been visited so far. Okay, now this is the kind of crazy behavior that you get with Tabu Search, and that's what I love about Tabu Search. It just go up and down like crazy. Okay, so it's very interesting to see what it does. Okay, so this is on a resource allocation problem where we are trying to minimize the violation. So the y-axis here are violations, and these are the iteration over time. And what you can see is that this objective function is going up and down. You get this good trade-off in trying to escape and then trying to focus on trying to find a good solution. And in this particular case, you see at the end, we find a violation of 0, so we find a feasible solution to this particular problem. Okay, and it takes 160,000 160,000 iteration. Okay, so this is zooming about the last set of iterations here, and what you can see as well is this kind of very, very chaotic behavior of Tabu Search. But in a sense, you go up, but you always, go down reasonably soon afterwards. And that's typical behavior of Tabu Search in this particular case. This is a graph coloring application where you try to minimize the number of colors, using satisfiability as a subroutine. And once again, you see this behavior, kind of chaotic behavior where you go up and down, and so on and so forth. Okay? So that's what I wanted to talk about today. Next lecture, I will focus again on Tabu Search and give you how you can actually implement this, because so far it has been at a very abstract level. But there are many other meta-heuristic that have been implemented and proposed. Variable neighborhood search, guided local search, and colony optimization, hybrid evolutionary algorithm, reactive search, scatter search, plenty of others. Some of my colleagues are going to be completely upset with me because I forgot to include their favorite ones, but I did these slides at 5 a.m., so bear with me. But essentially, they are, once again, this is an introduction. I gave you some of the principles. There are many other ones that you can actually study. Okay, see you next time for more on Tabu Search.